Okay, today we have Dr. Abhijit Mahalanobis. I've known Abhijit for, I think, around 20 years.
Yeah.
It's been a long time. Most of the time that I've known him, he was a senior fellow at Lockheed Martin, and I don't know if you guys know the Raytheon fellows and the Lockheed. It's a huge deal to become a fellow at one of these large companies. There are not many of them. So Abhijit's in the area of computational imaging, deep learning, signal processing, imaging, that sort of thing. He got his undergraduate at UC Santa Barbara, Carnegie Mellon for master's and PhD, and it's been a real joy to work with Abhijit over the last number of years. So with that.
Thank you, Ron. Thank you very much. So it's truly an honor to be here and a pleasure as well. And just a little bit about myself. I see Dr. Dave Brady here. I just met Dr. Mansooripur. I feel privileged to be in this audience, and thank you all for coming. And so I will tell you a little bit about myself, why it's Lockheed Martin. You'll have noticed that I am actually now a faculty in the EC department over here. I just joined this fall, and I have a really checkered past. I say. I started out straight out of college here at the University of Arizona. I was young, much like you guys, in the EC department. But then Lockheed Martin was Martin Marietta back then. This is in the, I would say, the late 80s, early 90s. And some of my work on target recognition algorithms caught their interest. And long story short, I took a winding path through industry. I spent some time here at Raytheon. I spent some time quite a number of years, almost 25 years at Lockheed. And Ron was always on the government side of things, and I would hear of this, let's say, this god in the field, right? Focal planes. And then later on, as I worked at Lockheed Martin, I became involved with computational imaging. And of course, I knew about Dave Brady, and he's here in the audience. But Dave, you might remember our first project together on Lacoste. And so I learned from the master himself. Got to work with people like Mark Neifeld, who were active at the time. And so in Lockheed Martin, we were working on sensors and systems. And so computational imaging was of a lot of interest. The DARPA put quite a bit of money into it. And as an industry guy, I got to work with people in academia quite a bit. The folks in optics, but also people like Rafi Koifman and others who are more on the, Larry Karian, who are more on the machine learning side of things. So to tell you the truth, I'm more of a, I'm a, what's the word I'm looking, jack of things and not my master of none. So I speak some optics, but I'm not a hardcore optics person. And I speak machine learning, but the people in mathematics wouldn't accept me as a machine learning person, right? But my research is kind of in the interface of the two things. And so I retired from Lockheed in 2018, and I wanted to come back to academia. And at that time, for family reasons, University of Central Florida seemed like the right place to be. We were in Orlando, Florida. So I spent the last 4 years actually at the University of Central Florida. And even though I'm an EC guy, they put me in the Department of Computer Science. And so when I said I want to buy optics equipment, they said, what? You know. So I spent my 4 years there doing entirely algorithms because all they had was computers. Don't get me wrong, they treated me really well. Computer science, computer vision, and UCF is very, very well known. But I became, I'm a survivor. What did they call that? Survivalist. So in the computer science department, I was doing machine learning. But now that I'm back here, I'm very much interested in getting back to optics and hardware and working with the algorithm team, but also on sensors. So the reason I have this talk, even though I'm here with the Lockheed Martin title, is because I haven't done anything on computational imaging lately, but this is an interesting piece of work that I'd like to sort of review that was actually done about 5 years ago in collaboration with Todd Dubosc, who is at the U.S. Army Night Vision, and actually with NRL, the Navy Research Labs, Jim Waterman and Jonathan Nichols. So so the question that we were asking here is that, for wide area imaging, companies like Lockheed Martin, even now, use pan and scan systems, particularly for an application called IRST, infrared search and track, which is the challenge of trying to find very, very small, dim objects. And let us say they're not spatially resolved, but they're point objects that are moving at a large distance, and you want to find these over a large field of view, like a 180-degree field of view. And you may be on a moving platform yourself. Typically, threats like this end up being incoming missiles or military aircrafts at long ranges. So it's called IRST. The sensor typically is a scanning sensor with a gimbal. It's heavy and slow. The alternative, of course, is there I think the pointer, does it work? Let me see. There should be a pointer option here, right?
Yeah, there isn't.
Okay.
That's right.
Oh, that's the thing. Okay. Perfect. Okay. The other alternative, of course, is to make a large focal plane. This is dated. Back then, 4K by 4K was large. Now, of course, let me qualify this. I'm talking about infrared systems like long-wave infrared or mid-wave infrared. If it is the visible band, then this is not an issue because I think focal planes are not the limiting resource. And, of course, Dr. Brady's work, you've shown very, very high resolution, excellent wide area imaging. But for the kinds of systems that they're interested in, the focal plane can still be an expensive asset to have. That's one thing. And then the size and the form factor all feeds in. This may not be true today, but back then, let's say 6 years back, the yields for this large format focal plane was lower, and so the cost was a real issue, right? So sensing that there might be funding here, from a computational imaging standpoint, we said, wait a second, you're probably going to get the best possible result you get with a large focal plane, and you're probably going to get the worst possible result with that scanning system. Is there a role for computational imaging, in particular multiplexed imaging, somewhere in between these two extremes, right? We might be able to, for instance, give you persistence over a large field of view, but do that with a smaller focal plane array or fewer number of apertures. Well, the apertures, it depends on the optical design, but focal plane is the resource we're talking about. So it might be that you can combine multiple apertures and collect the image in an encoded fashion on a single focal plane, or you might be able to collect a wide field of view through a specially designed lens like Dr. Ford designs, the monocentric optics. So the optics wasn't our concern as much as the focal plane. How many focal planes do we need, and can we economize on that resource, right? So that's the question we wanted to ask. And, this is basically the same thing. So the question is, can we do some sort of proof of concept to show that there is a trade here that might be beneficial in terms of performance? And again, I'm going to clarify up front that we're not talking about a general purpose imager, right? We're talking about IRST, point sources being detected in clutter. And the key thing that you're going to trade is probably signal to clutter ratio in this trade space. Okay, in terms of how do you collect and what the multiplexing concept I'm going to talk about, we assume that we have got some sort of a multiplexed imager, and there are various works that people have done to make this happen, right? Where you take different fields of view and you superimpose them on a common focal plane, and each field of view that you're looking at has been encoded in some fashion. The light comes in through the optics. Some sort of spatial light modulator is either encoding that field of view, or you're combining these fields of view with different weights. A very simple concept like this would be, let's say that there is, this area that you're trying to image, and you could do this with one focal plane this size, but if you had a smaller focal plane, roughly, half the size in each dimension, so 1/4 the number of pixels, you could, in this trivial example, come up with an optical collection mechanism that would point this focal plane in 4 different directions. That would be scanning. Or you could open up or collect 3 of these quadrants simultaneously with some encoding scheme and get a measurement like that. Well, actually, with these 3 on, I'm implying that it goes to some other measurement. In other words, that this particular one has persistence over 3 of these fields of view because you're combining 3 of them into any one measurement, right? And it ends up implementing a simple equation. I mean, this is, it's kind of obvious when you think about it. You're going to collect 4 measurements. Each one is a linear combination of the 4 underlying subfields of view, right? And I'm not going to belabor about the optical setup that does it, but I'm going to talk more about what happens on the signal-to-noise ratio and on the decoding side of things, right? Any questions about this? All right. So the idea, again, is that we are assuming that we have a smaller focal plane than the total field of view that we are trying to capture. And if you go through each one at a time, that would be scanning. If you can superimpose and collect multiple views, that's the multiplexed data that we're collecting. Okay, so now let me tell you about the data and the collection that we did. So I apologize, I don't actually have a picture of the actual apparatus that was used to do this, but I can tell you where it was done and what we did. This is actually looking over the Chesapeake Bay from NRL. So, you know, they have a very nice facility out there. You can bring out, I'm sure, Ron, you've been there. You know, there's a nice place where you can mount the sensors and collect data. So what we did is we wanted to do this with infrared. And even though I was at Lockheed, the resources are limited when you come in and say you want to do computational imaging. So they didn't give me any cooled sensors. They said, well, here's some uncooled long-wave microwave bolometers. I got 6 of them. So I said, okay, fine, let's go work with those. So imagine these, and so each of these long-wave IR microbolometers was capturing about 512 by 640 kind of images, and they had about a 20-degree field of view. So we rigged them sitting on a what do you call these things? A frame or something like that, like a mount, right? Looking in 6 different directions, and between them they covered roughly 100 degrees or so, with slight overlap between them. All right. And then my team, I had really good engineers and everything there. They figured out how to collect all that data and store it. But the interesting part of this is really the target. So Jim Waterman, who has since retired, had a friend who was a crab fisherman. And this is a true story. And this friend of his has that boat. It's a crab fishing boat. And Jim found out a way to pay him through NRL to go out there in the middle of the sunshine, drink beer, sit there, and wait for commands. And on top of that, and the reason you see this point up here, there's actually a mast on top of that boat. And on top of that boat is a hot iron that's radiometric, so that you can control and dial in the temperature. And so the data collection was done by asking the gentleman to go out to different ranges, go out to 1 kilometer, 1.5 kilometer, 1.8, 2 kilometers, and so on. So he would just sail his boat, then he'd go left to right, right to left, or he would just sit there. He got beer out of it. I don't think he actually got paid, but he got. But we would call him up and tell him, crank up the temperature to 100 Kelvin, or crank it up to 70 Kelvin, or something like that. I mean, centigrade, actually, not Kelvin, centigrade, right? And so that was what we were collecting. And the goal was to mimic from this data what would happen if we had a steering sensor, and so these, if you can imagine that we have one large focal plane that's equivalent to collecting all this pixel. We didn't do any mixing or anything, that would be our steering. If we were to go through each one of these, so if we just had one of these sensors and we assumed that we only got a frame every now and then from each of these sensors, and sequentially that would be emulating scanning. And then if we took this data and then did some mixing, added some noise, that would be our emulation of multiplexing. Okay. So now, this kind of shows you what we did with the data. So once we had the data, So we have 6 cameras, right? And each one was outputting data at 30 hertz. If you select the frame sequentially, right? So you take the first frame from camera 1, then you take the second frame from camera 2. Well, let's put it this way. We're trying to simulate revisit, right? So if you've got a scanning sensor, you're going to scan the whole thing and come back. So what we're trying to do is emulate that in the scanning process, we end up with just a 5 hertz revisit rate, right? So by taking one output and taking every 5th frame, basically we can emulate a scanning sensor's revisit rate of 5 hertz. Now then, if we just pretend that it's a steering array, right? We want to compare apples to apples, right? So the steering array could give us 30 hertz in all 6 channels, but instead of that, we're saying that we're going to use time and the sampling rate and the frame rate as our constraint. So over the time that it takes to scan, we're getting 5 additional frames for every location. So we can integrate these frames and increase our signal-to-noise ratio, right? So that's what we're doing over here, is that we're taking 5 frames and averaging them. Of course, we have to assume that during that time the target hasn't moved and there's been no real vibration and everything. But basically we're saying that, hey, look, the parallel system is always going to be able to give you, for the same integration time, a higher or better SNR, right? So that's our parallel array. And then for the multiplexing emulation, what we're doing is we're saying that we're going to make multiplexed measurements looking at the 6 fields of view and collecting one multiplexed frame. But then we're going to need to make 6 such measurements to decode that, right? So what happens with the multiplexed ones is that we're going to take an SNR hit when you multiplex them and make a measurement. But then think of this as a flowing buffer, like a rolling buffer, right? We can do that also, so the multiplexed encoded frame and decoding can happen once the pipe fills up, also at 30 hertz. So that means that the decoded frame can be aggregated again 5 frames at a time, and some of that SNR can be brought back. So timing-wise, this is kind of the scheme. This is for the scanning emulation, right? So this is a single output frame. Then you get 1 frame from camera number 2, 1 frame from camera number 3. So we're assuming that as the sensor scans, we're going to get a frame from each one of those cameras staggered in time. And the time when you come back to revisit the first place, you're only going to be able to see that the field of view at 5 hertz. Make sense? Right? And then this is what we're talking about with the parallel steering concept, that assuming that everything is being looked at the same time, if we also say that we just want a 5 hertz output from this, and of course then we can increase our SNR by integrating frames, right? So that's the benefit of those two. And then for the multiplexing, this is kind of what's going on. So we are making, so the individual cameras are doing what they're doing, but at the end of, so we are basically going to make encoded measurements. This is where the encoded stream is coming. These 6 camera views are being mixed optically, and we're getting 6 encoded measurements. But then we have to decode it, and so a decoded frame comes out over here, right? Now, once that pipe has filled up, we can keep on, like this green line shows, we can keep on taking 6 measurements consecutively, right? And keep on decoding those so that a series of decoding frames can also come out with a certain delay at 30 hertz. And then we can always integrate these decoded frames and again recover some of the SNR. So what you're getting out of this is similar to what the parallel array is doing. That's how you're getting the persistence, but it's coming slightly later in time because you've spent time acquiring the measurement and then decoding it. Sorry about that. Okay, any questions about the 3 schemes so far? Okay, all right. So now, once we have those 3 schemes, we're going to try and find that hot spot, that flash in each one of those things. Not the flash, I think it was a soldering iron of some sort, but it had its temperature control, right? And the algorithm, too, is not important here, right? So one can throw a lot of complicated algorithms on it, and to some extent, your results are a function of how clever your algorithms are. So to be honest with you, we didn't want to, let's put it this way. What happens in a company like Lockheed and probably in other places is that the sensor folks go out there and make a beautiful sensor, right? And then, but they didn't talk to the algorithm guys. And the algorithmists get the data, and they have no idea how the sensors worked at all. They got an image. And they do their algorithm and show really good results. But at the end of the day, when you put that two together, you put it in the system, and it mistakes, let's say, a pedestrian for a bicyclist, and the car runs it over or something. You never hear the sensor guy being blamed for it, right? It's always the algorithm guy's fault. So your algorithm didn't work. So we said up front, we're going to use a dumb algorithm. Don't ever use this in real world, right? So we said, it's not about the algorithm. We're going to only try to see the effect of some signal-to-noise ratio. So this is just the raw data that's collected. It has some sort of a pixel distribution. And then what we're doing over here is just running a simple Laplacian of Gaussians. All that does is that if there is a hot spot in there, right, it's a derivative operator. It's going to keep the hot spot and sort of give you a good peak, local peak, and then you can do a threshold detection, and you can say, okay, nobody in the real world would use this as a detector, but for the purposes of what we're doing, we're just going to do a threshold detection on this, right? The benefit of using something like a Laplacian is that it takes out the bias averages, and you lose slowly varying contrast, and all of that's gone, so the local value is not going to change anything, right? And if you look at the histogram, of course, it's going to be Gaussian. It's very likely Gaussian. Loosely speaking, very loosely speaking, central limit theorem applies and all that. But what we're looking for now with the threshold detector is things that are in the tail, right? So we're looking for large values because this is the hotspot is what we're looking for. And again, these are unresolved small hotspots. So I'd like to make sure that it's understood that this is not a general purpose imager. My goal is to find small targets like you do in IRST. And so this hotspot detector makes sense just from that application-specific standpoint. But if I do get a hotspot, it's going to be something that's many sigmas away from the main distribution of gray values that you get out of this. So there is a very nice theorem called the Fisher-Tippett-Gedenko theorem. I hope I pronounced the name right, but it's called extreme value theory. And it's widely used to study the statistical behavior of extreme values, like extreme weather, right? Extreme temperatures, let's say, or extreme floods, like a 100-year flood or a 200-year flood. And this statistic, this extreme value statistic, was actually made popular by the insurance industry because they were always interested in finding the tail of the event, right? So, but the theorem underlying distributions like the Weibull distribution, Gumbel distribution, Fréchet distributions, they are very well understood in the statistics thing. And what it essentially says in a nutshell is that it doesn't matter what the primary distribution is. It could be Gaussian, Rayleigh, Maxwell, whatever it is. Behavior of your samples on the tail, regardless of the original distribution, the behavior of the samples on the tail follow the extreme value distribution, right? So if you were to take the extreme values from any statistical distribution, they can all be fit to the Weibull, Gumbel, or the Fréchet distributions. It's called generalized extreme value theorem. So this is a very nice result from statistics because what it allows us to do, what you're seeing on this plot is the results of thresholding this. All those red dots that you see, those are the values that I've taken by applying a threshold. And then if you go back to this Gaussian distribution, they all occur kind of in this range over here, right? Now, if I then look at these extreme values and look at their distribution, you can see that it has kind of a shape like that. And you can try and fit different parametric distributions to it, but the one on the left, which is here, is the generalized extreme value distribution. So it's parameterized by what they call a trend parameter, which is akin to the mean, and a shape parameter, which is akin to the variance. That's a very good fit. And then on this side, you're seeing an attempt to fit other kinds of distributions to the data. Normal, Poisson, Rayleigh. None of them fit as well as the EV distribution does, right? Okay. So long story short, using that statistics, we can then come up with a ROC curve to show how we... So now the thing is that we are applying a threshold. How likely are we to detect that hotspot versus mistaking false positives for the target, right? And you can plot that out as ROC curves. And there are 3 lines here that you see. The green is the multiplexed result, the red is the parallel result, and the blue is the pan and scan. So what we're saying is that we have put everybody on the same scale, right? Everybody's giving a 6 hertz output, but they're giving persistence in different ways, right? The steering array is giving you persistence all the time, but also giving you higher SNR. The scanning system is giving you one look every 5th frame, basically. And the multiplexed one is giving you persistence with some sort of an SNR. I'll show you that's lower than better than pan and scan, but lower than parallel system, right? And what you see here basically is a function of range at 1 kilometer, 1.8 kilometer, and then this is with different temperature settings. Is that, let me just show you over here. At the close range, relatively 1 kilometer, there's no difference in these systems. We are in what you would call a clutter limited scenario, and our clutter was C clutter, very benign. There's no additional noise that we've added yet. So in clutter limited conditions, there's not much difference between all 3 schemes, right? Because you have plenty of signal to noise ratio. But here, as you go out a little bit further and you lower the temperature, this is aggregated over 70 degrees centigrade and 50 degrees centigrade, whereas these are both at 100 degrees centigrade. A little bit of a separation occurs. The parallel array, the higher probability of detection, I'm sure all of you know an ROC curve, the higher the probability of detection, the better. The lower the false alarms, the false positives is better, right? The red curve, which is the parallel array, gives you the best possible performance. The scanning one gives you lower performance, and then the green one, which is the multiplex system, is somewhere in between. But the separation is not as dramatic because we are in clutter limited conditions. This is the same ROC curves, but instead of using raw data, we fitted those parametric distributions, the extreme value distribution parameters. So we took the data, figured out what the trend of the distribution would be, what the shape of the distribution would be, the kind of akin to the mean and the variance. And we can plot out the same curves. They just come out cleaner because we're not using the raw data points. You can see the same thing. The parallel system gives you the best probability of detection. The pan and scan gives you the worst, the blue one, and the green is somewhere in between. This is just on the log scale. Now, the separation is not hard, but there's a message emerging, right? What we've done here is basically said that you could take 6 arrays and look everywhere all the time. That would be one way to do it. You could take 1 array and pretend like you're scanning, or you could take 1 array and put a multiplexing optics in the front, collect frames. You're now recovering some of that SNR because you can take advantage of the frame rate and decode and get back some of the performance, right? So now we add noise. So now we're going to look at the noise limited performance on this. So long story short, we add noise either to the single frame or basically we want to emulate that this noise is added as close to the focal plane as possible in the scheme, right? So we've got to add it. In the case of the scanning or the parallel one, it's easy. You just add it directly to the data frame. But for the multiplexed one, we have to do the encoding first because we're assuming that the data that's coming in is going through the optical process and getting mixed and encoded. And so when you collect the data on the focal plane, the noise has to be added to the multiplex data, right? So that's why the noise is added after the encoding stream. And then, of course, you decode it, and then you look at what happens after that. Okay, now some interesting things show up. Okay, now at the range of 1 kilometer, as always, even with noise added to it, the parallel array, the red line is the best. And then with the pan and scan, this blue line is considerably lower. Now that you have added noise to so you've increased your sensor noise. But the multiplexing, if we just simply decode it, right, without aggregating the decoded frames again, we can remember that we can decode the multiplexed one with a slight delay and also get 30 hertz out of it, right? You're just taking 6 frames of the encoding and then staggering them and decoding them and getting decoded frames at 60 hertz. But now if you have a choice, you can either take the decoded frame and do it, or you can aggregate these, aggregate the decoded frames and recover some SNR. And so what ends up happening, this green line shows you what happens, this multiplex stacked, meaning that you're using multiple encoded measurements and aggregating them to build up the SNR, then you get the green line. And now the message is a lot clearer, that there is a role here, perhaps, for the multiplexed computational imager to economize on the focal plane and give us a performance that is considerably better than the scanning system, but cost and resource-wise, at least from a focal plane standpoint, it's comparable to the panning scan and pan. And this is at a farther range, same kind of thing. This is at 1 kilometer, this is at 1.8 kilometer. Again, the green line lies somewhere in between the other two extremes, right? How am I doing on time? 15 minutes? Okay.
Is that okay?
Oh, yeah. Let's see. We will... And then we did the same kind of thing. So the first noise was signal independent noise. It was just noise added to it. And then we also wanted to do signal dependent noise, which is shot noise, basically. Same kind of trends emerged when you do that. At a range of 1 kilometer, the signal is plenty strong, so the shot noise is not as bad. But when you are farther along, the signal is weaker, and you get this green line between those two, right? And lastly, okay, so the last part is about this horizontal axis. This is false alarm. So we have 110 degrees. So I should have explained this before probably. The vertical axis is probability of detection. We all get that. But the horizontal axis is about the false alarm. So let me tell you what that is. So what's important to the user is they're panning and covering a large area, right? So you want to get false positives. Well, as few of those as you want, as you possibly can. But how do you measure that, right? So it has to be some sort of a rate. So typically we do false positives per square degree. So if the imager, in this case, we're covering is 110 degrees or 120 degrees field of view, so you count the total number of false positives you got over that and divide that by the total square degree, so that's false alarms per square degree. But in addition to that, from a human operator point of view, the person is staring at this thing for a long period of time, right? So it's not just the per square degree, but how many over time do you get? So we had a lot of discussions with Jonathan Nichols and NRL about this. And Ron, you're familiar with these things. They basically came up with, false alarms per square degree per second, I think was the thing. So it also matters how many of these are you getting per unit time, per unit area. So a lot of that that kind of measurements was important in terms of understanding these traits. I won't belabor too much about that, but I think it means a lot to the people who study those kinds of human factors aspects of all of these kinds of things. Okay. Then the last few charts are more of... So we said that our detection strategy was very simple. We were just running a difference of Laplacian of Gaussians and doing a peak detection because I purposefully did not want it to be the algorithm's fault. But that said, there is a question that begs answering, is that we're doing peak detection. Is it better to integrate the frames and then detect? Or do we do detection on the individual frames and then aggregate those detections? Is there a trade-off there? And that's what you're seeing over here. On this side, this is the integrated frame being thresholded. On this side, individual frames were thresholded first and then integrated. When the sponsor asks you a question, you do your best to answer it always, so that was in that category. And what came out of that is these ROC curves. I'm just going to quickly explain these. Is that these are the previous ROC curves that you saw. These were all integrate the frames first, then detect, right? So you're taking a much more improved SNR and applying a threshold. Over here, what we did is the same scenario, same data, except we thresholded individual frames, got the detections, and then added up the detection scores, right? So for that, you have to sort of do a little bit of bookkeeping to make sure it's the same detection. But the ROC curves in the end didn't change a whole lot in terms of performance. At the same false alarm rate, we got very similar probability of detection on the green curves. You're comparing the green curve here to the green curve. And this is the one from the integrate first, then detect. And this is the same thing, but done at two different ranges, 1.8 kilometers. So in the end, our conclusion was that it's probably, at least for the simple-minded detector, it probably wasn't going to make much of a difference. That's caveat. Sophisticated algorithms should do even better, is my point. Okay. So in summary, let's just say that in what we found with this data, caveat its limitations, it was long-wave IR. We emulated noise by adding it. That kind of thing. It's uncooled sensors to begin with. We didn't really model the optics per se. There's some losses in the optics that have to be accounted in all this. But to the extent that everything was compared apples to apples, it is obvious, we always knew going in, that we are not going to be able to beat the staring wide field of view imager, which gets you the best SNR per pixel. But what we're trying to beat is the other guy, which is the scanning system, right? Can we beat the scanning system? And the conclusion is that at least in clutter-limited conditions, yeah, you can, but it may not be worth it because the performance doesn't warrant it. But if you are in an SNR-limited condition, then there is a much wider gap to fill, and there is probably room there. And oftentimes in these IRST applications, you are in an SNR-limited condition just because of the form factor and constraints under which you have to operate. We also looked at different detection schemes to reduce the false alarm rate. So to pick up on this, now that I'm here and again able to work on this kind of stuff, it would be good to look at SNR limited conditions under a short noise model that's representative of mid-wave sensors, because this is, for IRST applications, they may actually need mid-wave sensors more. That'd be something that, Ron, I might want to ask you, is what do you think is the right band for those kinds of things? Then optimal detection algorithms in coded space, and there's some room for collaboration with computational imaging folks for that. And then compare the performance of multi-frame detection schemes, the effects of SNR gain used using frame integration. So we have assumed frame integration, but if we were to do it in hardware, then we would like to get the data instead of emulating it to actually crank up the integration time on the sensors and collect data at different integration times and see if that all really bears out. So with that, I think I'd like to end over here and see if there's any questions.